Okay, so now we move to part 2 of the course, which is about functional and logic programming. So we're going to see more advanced mechanisms that Lean provides, and Lean's calculus of inductive construction provides the logic of Lean, beyond just the quantifiers and connectives and equality. You know, for functional programming, that's recursive functions, that's induction, but also some other mechanisms like records, type classes, pattern matching. We're going to see more pattern matching than we've seen before. So this lecture is typically one that is a bit more relaxing than the previous one. So we're going to go at a slower pace. We're going to see things that we've already seen before, and we're just going to consolidate you know, what we've seen in the first 3 lectures, which is good. We're going to catch our breath, literally, or at least figuratively. Okay, so we'll start with the inductive types, which we've already seen. So in particular, we define, you remember, the type of natural numbers. Well, this is the built-in one from the library, so I didn't click on the one. Oh, and now I've lost my file. I'll find it again. Right, so this is the built-in one. It has the zero and suck cases as its constructors. And the idea is that this command introduces not only a type nat and not only these 2 constants, zero and suck, but also some very important lemmas that tell us that zero is different from suck, for example, right? I mean, all these lemmas that tell us, I mean, basically we want 2 to be different from 3, to be different from 4, and so on, from 0. And we also don't want any other numbers, right? We don't want infinity or -1 or epsilon. We just want 0, 1, 2, or successor of 0, successor of 0, and so on. No more, no less. And this motto is, well, the motto that captures this best is no junk, no confusion. So no junk means we don't have -1, we don't have epsilon, and no confusion means that 0 is always different from successor of something, right? So different constructors lead to different values. So it's very much what you see is what you get. So you look at this definition, and you know, every term you can build using those constants is going to be a distinct value of type nat, and that's it. Okay, and also one last thing is we don't allow infinite values. So we don't allow suck of suck of suck of suck, you know, dot, dot, dot. Well, first we cannot type it like this, but also, I mean, if we write it as an equation, write x equals suck of x, that is impossible, you know, that will be false. Okay, there's a concept called co-data types where this is possible, but we're not going to see co-data types in this course. We're going to focus on standard inductive types or data types. And the other types, well, this was just natural numbers, but I mean, we've seen other examples already in the first lecture, so I'm not going to dwell on this. So let's move on to structural induction. So structural induction is a generalization of mathematical induction. You know, the induction that has a base case and a step with, you know, k equals 0, k equals n implies k equals n plus 1, right? The standard induction, the most basic induction you have. So structural is the same, but, you know, for any inductive type that Lean can define, not just for the natural numbers, right? And so for natural numbers, we have, well, we have exactly what I just said. You have the base case, right? You want to prove P of n for all n. Well, you need to prove P0. And then you need to prove that for all k. I'm using a different name here, but I could reuse n. So for all k, P of k implies P of k plus 1. And this here is the induction hypothesis. And of course, I could write suck here. I could write nat suck. So I'm going to use the syntactic sugar while it's there, right? For lists, you have P of the empty list, and then, you know, to prove a cons, remember this is the syntax for cons, a list where the head is y, and the tail is ys, the rest of the list. And the induction hypothesis is about ys. So you don't have an induction hypothesis about y because it doesn't even have the right type, right? So P of y would not be type correct. Okay, so we get induction hypothesis only for the type on which we're doing the recursion, or which is recursive with itself. And then we start with a first proof, which is that the successor of a natural number n is different from n. And we have to do this by induction, and we see it because there's an n in it, right? We need to prove something for infinitely, many values. So, I mean, if this started with 0 here, or where 0, I should say, then we would not need an induction, because that would come from no confusion, you remember? But here, suc of n different from n, we have to do it by induction. And you see it's a very easy proof. You have two cases. I'm going to show. This window really loves to go the wrong place by default. It's amazing. And we start, and at first we have to prove that 1 is different from 0. That's quite easy. I do it with simp here, but there are probably tons of ways of proving this. I wonder, maybe CC can do it. Oh, yeah, even CC can do it. And then here we have to prove, yeah, okay, it looks complicated, but it turns out simp with induction hypothesis does the trick, so I'm not going to ask for more. And let's see if CC does it. CC does it. Because CC does know about the hypothesis. It uses everything it sees in the goal to try to derive a contradiction. Okay? Now, when we do induction, sometimes we're not happy with the names that Lean generates for us. Actually, I should say Yannis generates for us, because it's Yannis Limperg who implemented induction prime here. So if you want to complain about it or praise his work, then you know who is your Ansprechpartner, your Kontaktperson in Dutch. But he's not Dutch, I don't write to him in Dutch. So here's the induction as usual, but now with the case tactic, it's a kind of special tactic. I can choose which of the two cases I do first. And I say here, oh, I want to do suc first, and I want to rename the two variables m and uppercase IH. And then we zoom onto the goal, and then this is what we see. We prove it, and then we say, oh, I want to do the other case now. So often we're going to use this case notation because it's more explicit. We see it's more readable. The proof is more like a human proof. We say base case colon, right? We don't just put some stuff there. And although the system helps us, we can use Lean to see, oh, where are we, and so on. It doesn't hurt to have a bit of redundancy in our proof scripts for readability, especially when you come back to them, years later, and you're like, what was I doing here? I mean, it's like programming, ultimately. What we're doing is very similar to programming. Okay. Oh, I think this is the wrong way to quit.